All right, can everyone hear me okay? Coming through? Great. All right, welcome everyone again to another week of the Conservation Sciences seminar series. I think everyone here knows the drill, but before we get started, if you have any questions throughout the talk, feel free to drop them in the chat or we'll get to them in the Q&A after. Because we got a holiday weekend with Easter coming up, we'll probably have a slightly shorter talk, roughly around 30 minutes, so plenty of time for questions or to end our week early. So with that, it's my pleasure to introduce our speaker for today, Melanie Dickie. Melanie is a caribou recovery ecologist at the Alberta Biodiversity Monitoring Institute, and she's also a PhD candidate at the University of British Columbia, Okanagan. Melanie works closely with multi-stakeholder groups to design and implement collaborative landscape-level mensurative experiments. Melanie is interested in understanding the mechanisms in which human habitat alteration and climate interact to influence the predator and prey community related to caribou declines in Western Canada. With that, Melanie, please take it away.
Awesome. Thank you so much. Can you hear me okay? Great. Thanks everyone for being here, especially just before a long weekend. Where I am, it is a long weekend already, but I'm more than happy to be here talking to you guys about this work. So thank you very much for inviting me. My internet is a little bit unstable, so while I'm giving the presentation, I'm going to turn off my video so that I can make sure that the video or that the presentation is coming along. So I'll go ahead and do that now, but I'll turn my video back on when it's the question and answer section.
Great. And Melanie, it does sound like it's maybe a little bit quiet for some folks. I don't know if there's any way to improve the sound a little bit.
See what I can do here. I'm not full blast. I'll just talk louder and hope that that's okay. Okay, so today I'm going to talk about a paper that I did as the first chapter of my PhD program. It's called Resource Exploitation Efficiency Collapses the Home Range of an Apex Predator. I'll start off with kind of some of the most fundamentals of ecology, the distribution and abundance of species, which is really the building blocks of a whole bunch of what makes up ecology, community ecology, for example. So it's one of those most basic building blocks of ecology. For any given species, one of the drivers or ways to think about distribution and abundance is through the formation of home ranges or territories. And this was really driven home for mammals early on by William Burt. And a home range is the area in which a species or an individual needs to take up and occupy in order to survive and live its life. The territory, if a territory exists, is the defended portion of that home range. So all individuals will have some semblance of a home range. Even if they're nomadic, I would argue that the home range is just the area that they occupy to make a life. Some of them are more stable than others, and the territory for some species is where they defend. In any case, distribution and abundance is made up of this patch use or habitat use and the movement of those organisms. And it's really just different scales of thinking about distribution and abundance. Home range size can be influenced by a variety of factors. The most kind of basic is the intrinsic factors. So, for example, the sex of that animal, males versus females. Males will typically, but not always, have a larger home range than female conspecifics. Body size is also important. Larger animals typically need more space to survive, but often we think about that because they need more resources. So that brings me to the extrinsic factors. There's a variety of them, but the one that we think about the most is resource availability. If you need more resources to live, you need more space to live, typically, depending on how those resources are distributed about your environment. Some of the early seminal work by Codric, Brown, and Brown in 1978 with hummingbirds looked at territory size on the y-axis here as a function of flower density, where flower density is the metric of resource density, or the availability of resources for hummingbirds. And they found an inverse relationship between territory size and resource density, or flower density, where when you have more resources available to you, you can occupy smaller areas to make your living. But life is a balance between the energy you intake and how much it costs you to get that energy. So it's a balance between acquisition and expenditure. And so resource availability needs to be thought about with this balance in mind. Not only is it about the density of resources, or how much energy you can acquire, but also how much energy it takes to get that resource. So one of the questions I wanted to ask with my PhD work was, does resource exploitation affect home range size? We think about this energy density quite a bit, but what about how costly it is to move about your environment and acquire those resources? To do that, I used the Western boreal forests of Canada as a study system. And I did that because humans have very much changed how animals use this landscape. Here I have photos of seismic lines, which are used to explore for oil and gas reserves underground. Operators will clear these long, wide areas. They're usually 8 to 12 meters wide historically, to bring equipment through the forest, send seismic shocks down into the earth, and when those seismic shocks return back, they're able to map the reserves underground. Many of these seismic lines were created back in the 80s and before the 2000s. And yet, because of the way the soil was compacted and the removal of the seedbed, many of these features have not regrown. And these features are quite omnipresent through Western boreal forests of Canada. I don't usually do videos in these kinds of seminars because I'm afraid that it's going to mess up, but I wanted to give you guys a sense of what it looks like. So I just made a quick screen cap of Google Earth and zooming around. So I'll play that as I talk, and hopefully you can kind of get a glimpse of what it looks like. So here I'm just going to zoom in on Alberta, a random area in northwestern Alberta. And as I zoom in, you see those seismic lines and other linear features start to pop up. So when I say there's a lot of them, I quite mean it. Some of these features are in really, really high density, some are wider than others, but they form this web of linear features through what looks to be an otherwise relatively intact landscape. We look over in the northeast of the province of Alberta, we see the same kind of pattern. So it's not that I just zoomed into a given area I knew had these features. We zoom in really close. Some of them, these are called low impact seismic, are as close together as 50 meters apart. So they're quite common across the landscape. They take up a pretty small area specifically, but many of the critters on this landscape really like to use these features, wolves in particular, and admittedly humans. I mean, when I'm out there walking through this study system, I'm not going to trudge through the bush and bushwhack. I'm going to use these linear features to travel on because it's much easier to do that. And we know that wolves do the same. So here I'm just showing you GPS collared wolves. There's two here, one on one side of the lake, one on the other side of the lake. Each of these yellow dots is a 5-minute GPS location. And just from the raw telemetry data, the GPS locations themselves, you can start to actually see these linear features on the landscape. You could almost map them just from looking at these images. So they're pretty omnipresent across the landscape. And wolves not only use these linear features, but they actually move 2 to 3 times faster on these cut lines. So we know that these features are facilitating the movement of wolves on this landscape. So I wanted to use this system to ask the question, what is the relative effect of resource density and resource exploitation on wolf home range size? I say home range and not territory because I didn't specifically look at the defended part of their home range, the home range in general. So contrasting resource density available to them, the ability for them to move across that landscape, or the interaction between the two, looking at whether or not the ability to move and exploit that landscape depends on the underlying resource density. I did that using 142 GPS collared wolves from 2011 to 2017, spanning across British Columbia, Alberta, and Saskatchewan. The 3 provinces don't matter in particular, but what they do is provide quite a gradient in linear feature density. So each of these seasonal wolf home ranges here, shown for each individual wolf, is colored by the underlying average linear feature density. And we can see that over up in British Columbia, over here, there's generally higher linear feature density, though some wolves did have access to lower linear feature density. Whereas in Alberta, it's also quite high, not as high as BC. And then we see the underlying gray is linear features, and it largely drops off when you move into Saskatchewan. This weird kind of pattern that you see to the south is just the boundary of where they're drawn. That's not real, but this contrast here is very much real. And that's because once you get into Saskatchewan, the oil and gas reserves is so far underground that it's not really economical for exploration, at least not yet. So there's not a whole lot of oil and gas exploration over into Saskatchewan. Most of those linear features are low-use human roads rather than seismic lines. Very similar, but created for a different purpose, and sometimes have truck tracks on them, for example. None of these linear features, or very few of these linear features, are high-use roads. There are a few highways that go through here, but the majority of this gray that you're seeing are these seismic lines and low-use roads that don't have a whole lot of human activity on them, but are very much used by wolves. Up in the green panel of the inset map, I'm just showing you delta EBI, which is a measure of habitat productivity. So what I'm showing here is that not only do we have a gradient of linear feature density, which is what influences movement rates of wolves, but we also have quite the gradient in habitat productivity at the same time. So from that, we can start testing the relative influence of resource density and exploitation. For resource density only, I use that delta EBI metric as a metric of primary productivity which is a proxy for moose density. So what delta EVI measures is the Enhanced Vegetation Index. It essentially compares the greenness in winter when there's no leaf out and it's just conifers to the greenness in summer when the deciduous trees have all leafed out, and it's a measure of deciduousness. And we know that deciduous forests are a resource for moose in particular and other ungulates. Where there's more deciduous forests, we have more moose. Now that's kind of an assumption, so we wanted to test that. Here I'm showing you delta EVI again in the background with the greens. Darker green is more productive. And we also have aerial moose ungulate surveys that are flown from planes, aerial surveys. Each of the polygons are colored by moose density. And if we plot that out, we see that moose density increases as a function of delta EVI on average. Not perfect, but I'm comfortable with using this as a proxy. Now this part coming up isn't part of the paper, but we do recognize that moose aren't the only prey species for wolves. So here I'm just showing you that the density of deer, specifically white-tailed deer, in this system is also related to delta EVI. Where we have higher productivity, we see higher densities of deer. This is a completely different study that's also part of my PhD and is done with camera traps. For resource exploitation only, we use linear feature density as our proxy for movement capacity. So areas where there are more linear features available, that area is easier for wolves to get around. And then of course the interaction between the two to look at whether or not movement capacity matters more or less in any given resource density. I used an AIC framework to relate the home range size of individual wolves as a function of these three different models, very basic model comparison. I did account for study area as a random effect in that model, as well as pack ID, because I did look at individual wolves, but I included pack ID as a random effect. And with the AIC framework, we see the most support for the interaction between linear feature density and delta EVI for explaining the home range size of individual seasonal wolves. So going back to the question, that's supporting the interaction between resource density and exploitation for influencing home range size. And that begs the obvious next question of, okay, if both resource density and exploitation matter for influencing home range size, how exactly does resource exploitation affect that home range size? If we take ideas from optimal foraging theory, we can make one set of predictions. So here I just have a very simple depiction of optimal foraging where energy gain increases as a function of foraging time until eventually it plateaus where energy isn't being gained as the critter continues foraging there. But that's really, thinking about patch use, but what about how much energy it takes to get there? So we think about foraging time, but even Sharnov showed also travel time, how much time it takes to get from patch to patch. So again, bringing back those ideas of distribution and abundance are both influenced by movement and patch use. If we place our tangent line along this curve and solve for the optimal foraging time, where the curve meets that tangent line at the dotted dashed line, that's when it's optimal for a forager to give up on a patch and move to the next patch. If we decrease our travel time, we make that line steeper, and it now hits that curve at an earlier part. So we decrease the amount of time that it is optimal for a forager to spend in any given patch, because now it's easy enough for them to move to the next patch and get the most, that steepest part of the optimal foraging curve. This was tested by Cowie in 1977 with great tits, where he looked at time in patch as a function of travel time. So that travel time, he used an experiment where he essentially made it harder for them to access resources, and found that the amount of time that they spent in a patch was in fact influenced by the amount of time it took to travel from patch to patch. So when it was harder to get to a patch, or it took more time to get to a patch, they spent more time in that patch. So if we take these ideas and apply them to the home range size, what we would expect is if it's easier to move from patch to patch to patch to patch, that animal will diffuse across its landscape, and home range size will increase as they move from those patches or across the patches throughout their landscape. But if we go back to the ideas again of life being a balance between the energy you need to acquire versus how much energy it takes to get that resource, if we decrease the energy it takes to get from patch to patch, we would also expect that you need less energy to make a living, to make up that balance. And under that, what we would expect is home range size to decrease, because you can be more efficient and you don't need to diffuse across the environment, for example. So if we look at those two kind of theoretical backpinnings, they have contrasting predictions for what you would expect the relationship between home range size and movement cost to be. If we put it in terms of linear feature density and apply it to the study system here, what we would expect is sorry, I'm trying to get my mouse in the right spot here. Over here where we have higher linear feature density, under the diffusion facilitation hypothesis, you would expect higher linear feature density areas to have larger home ranges, because it's easy enough for those wolves to just move across their environment and keep spreading out. Alternatively, under the resource exploitation hypothesis, in areas with high linear feature density, you would predict smaller home range sizes. And that's because they are efficient at finding the energy that they need, so they don't need to acquire as much resources. They can kind of eat what they want to eat and just sit tight. So here I'm just going to show you home range area of the winning top model, the interaction of linear feature density and resource density, or delta EVI, as a function of linear feature density on the x-axis. I'll also show you the model predictions with scaled delta EVI. So essentially 0 is the lowest habitat productivity that we saw in the system. 1 is the highest productivity. Going from brown to green means we get higher productivity. And assume that also means higher ungulate density. So here's the raw data with those modeled lines on top of them. And what we see overall is a decrease in home range area as a function of linear feature density, which supports the exploitation efficiency hypothesis, but only in low productivity areas. So if we look at that green flat line where we have high productivity, what we see is that regardless of linear feature density, those home ranges are quite small. In contrast, if we start to lower the productivity of the system, we get larger home ranges when the linear feature density is small, but it declines as we get higher densities of linear features. So essentially, these linear features are allowing wolves to exploit a low density system, a low resource density system, more efficiently, and they need to take up less space to make a living. So what are the implications of that? First, I'll take a theoretical kind of look at it and argue that it provides a little bit of evidence of linking the functional and numerical response together. As a quick refresher on what the functional response is, here I'm showing prey consumption on the y-axis as a function of prey density. This is the type 2 functional response I'm just showing as an example. And we have prey consumption increasing as we have more prey on that landscape, but it asymptotes as a function of handling time. So at some high prey density, a consumer can only eat so much food, it needs to digest, and it doesn't actually continue to consume more prey. But if we increase the efficiency of that predator through the instantaneous search rate, we get that forager or that predator up to its handling time faster. The more efficient that predator is, the earlier on in this curve does it hit its handling time asymptote. And so by increasing the instantaneous search rate or the search rate in general of these predators, what I'm arguing here is that we can also decrease the amount of area that they need to survive, which means we can pack in more of those individuals. And that's where the numerical response is. We're getting more predators in that landscape because they're more efficient hunters, which links that functional and numerical response. Typically, we think of the link being that their output increases, but here we're also thinking about the amount of space they need to survive shrinks. Now, this would only be true, of course, if pack size remains the same, or at least if pack size does not decrease, because then we would just get more packs, but smaller packs, and that wouldn't actually change the density of wolves on the landscape. We tested for that the best we could and found no effect of pack size or no differences in pack size. But we didn't have the best information across the whole study area to be able to do that super well. We did the best that we could, found no effect, but that's something that I'd like to look into a bit more. Implications then for predator and prey interactions. So we typically talk about linear features making more efficient predators, so they can move 2 to 3 times faster on these cut lines, which means they have higher hunting efficiency because they're encountering prey more often. But now we're also talking about potentially more predators on that landscape, which is kind of like a double whammy to that prey species, where we have more efficient predators and there's more of them. But we haven't been able yet to test kill rates, and that's a big hole in the story for me, understanding how this increase in hunting efficiency and increase in predator density is translating to actual kill rates and predation rates on those ungulates. So that's something that I'd really like to see get done. One thing that I didn't mention when I was talking about that link between the functional and numerical response is we don't have great estimates of wolf densities in all of these areas, but anecdotally on that Saskatchewan-Alberta border, where we have that decline in seismic line density as soon as we get past Saskatchewan or into Saskatchewan, we do have data there on predator densities, and they do match our expectations where the density of wolves on the Alberta side is much, much higher than it is on the Saskatchewan side. Though there's some confounding factors there, and I'd like to test that better. For management, I like to work in kind of an in-between theory and applied ecology. So I'm always thinking about what this means for the critters on the ground. In Canada, one of the kind of biggest species at risk that we talk about almost daily is woodland caribou. This is the distribution of caribou across Canada. Almost all of these populations are in decline. Not all, but many, almost all. Boreal populations, this is where we were talking about in the green over here. So we were looking at areas overlapped by boreal woodland caribou. Caribou within Canada are a threatened species and are maybe going to move over to the endangered category for some of the designatable units. They've recently become extirpated from the continental United States, or the contiguous United States. They used to come down in here, and historically they actually very much lived in the US, but they've been receding northwards, and the last population down here blinked out in 2018. There have been 12 extirpations of caribou populations in Canada since 2000. One of the primary drivers of caribou declines is disturbance on the landscape. So here I'm just showing the mean recruitment rate for different caribou populations. So the number of calves per 100 cows. If you're creating more calves, you're able to replace your dying females, so your population is doing better. And what we see is that the recruitment rate declines with the amount of disturbance on that landscape. And most of the populations over here in the low recruitment, high disturbance area are actually from Western Canada, from the study system that I've been talking about. And because of this, caribou are very much a billion-dollar problem. And that's because not only do we have to do quite a bit of habitat protection to make sure they have protected habitat, but we have to do a whole lot of habitat restoration because many of these caribou ranges are already disturbed way beyond what the populations can take. And when we talk about restoration, we're largely talking about the restoration of these seismic lines that I've been talking about to facilitate return to forest cover, slow wolves down, and kick them off of these lines. So predation by wolves in particular is one of the proximate and key proximate causes of caribou declines. Their mortality rates are just very high, particularly for calves. And these linear features are implicated in those declines. There are hundreds of thousands of kilometers of these seismic lines within caribou range in Alberta and BC alone. And to restore these features, it costs somewhere in the realm of $10,000 per kilometer. So it's going to cost a lot of money to do the restoration work that we need to do. And it's also going to take a lot of time. Even as restoration starts to really roll out across boreal Alberta now, we're still only restoring about, a couple hundred kilometers of lines annually, and we have hundreds of thousands of them that we need to do. and then it's going to take time for the trees to regrow. So we can use the results of this work to prioritize where we do that restoration. Because what we saw is that linear features have a weaker effect on the home range size of wolves in productive landscapes where we've got lots of moose and deer, but a stronger impact in areas of low productivity, which is actually where caribou thrive, because they don't do well where there are lots of predators or apparent competitors. So what this tells us is that if we prioritize these low productivity areas, not only are we doing it in areas where caribou are more likely to occupy, but we're also going to have potentially the impact of expanding wolf home range sizes, slowing wolves down, making them lower density because they need to occupy larger areas to make a living, and doing it where caribou are. Now with that, I'd like to thank all of my funders. This was the amalgamation of 4 different research programs, GPS collar data. So lots of folks involved in this work, and I'd very much like to welcome questions. Please feel free to either type them in the chat as you usually do, or I'm happy to also take them audibly, orally, I guess.
Awesome. Thanks so much, Melanie. That was a really fantastic talk. Looks like Joe has raised his hand, so feel free to start it off.
Yeah, thank you. It's fantastic work. Some of the best evidence of how, linear features and how human anthropogenic effects can really affect or influence fundamental ecology. A lot of silvicultural prescriptions, at least in the US, and utility exploration or line cuts have remediation requirements. And I'm wondering if your work is changing any of that kind of contractual policy for new explorations where the onus is on the industry to actually remediate the feature.
Yeah, so a lot of the conventional seismic lines that I was showing, the wider, straight, long ones, nobody owns those anymore. They're just public at this point. So there's no obligation for industry to recover or restore those. That said, the regional industry caribou collaboration, First Nations groups and other industry have been so far at the forefront of doing that restoration work. There's now slowly starting to be a bit more government oversight on that restoration work, more prioritization, more funding programs to get the work done. And there's over time been a change in how they develop new seismic lines. So those really, really tight, narrow ones that I showed that you hopefully got to see, they're 15 meters apart, they're more wavy, they're sinuous. The low impact seismic lines, those are more common now than conventional seismic lines are. And that's partly driven because they wanted to reduce their impact on these systems, but also it depends how you need to map the underground. So these conventional seismic lines aren't created very much anymore because they've already kind of mapped everything they need to map at that resolution. That said, there's starting to be a bit more policy related things to make sure that they're restoring conventional seismic lines. Companies are starting to put out things like net zero disturbance. If they're going to create more seismic lines, they're restoring the same amount of seismic lines. It's slow, but they're getting there, and so far it's mostly been voluntary, moving towards policy.
Yeah, thank you. And just one quick follow-up. Are there stakeholders who don't want to see the restoration because the access then changes for whatever activities they might be interested in?
Yeah, so absolutely. It's not an easy conversation. A lot of these areas or a lot of these lines don't get used anymore, and those are the low-hanging fruit. But certainly there's trapper access we need to maintain because these have been in since the 80s and now they're established trap lines. There's indigenous communities that use these features to get around for hunting and recreation and cultural practices that we need to respect, obviously. So there's that. Some of these seismic lines do get reopened and eventually turn into roads or pipelines. So yeah, it's a bit of a mess.
Thank you.
Then Melanie, it looks like we have a couple questions in the chat. I don't know if you're able to easily see that, but if not, I'm happy to read it out for you.
Do you mind?
Yeah. So Danny has a question. Have you looked at how these linear features have altered lone wolf dispersion, particularly how lone wolves are navigating smaller but more numerous pack territories where you would expect the encounter rate of lone wolf with pack animals to be higher versus areas with less linear features within similar boreal landscapes?
Yeah, no, that's a great question. We don't have enough dispersals in the data to actually look at that in a meaningful way. One anecdotal thing, or two anecdotal things, I guess, is when I was using part of this data for my master's, one of the study areas was for my master's work. We did see dispersal along these linear features. Like they very much use them as dispersal corridors. So that's interesting. And then also the interpack aggression was the primary cause of death of these wolves and almost the only cause of death. There was a few that were shot, for example, but very few. Most of the animals that died because of interpack aggression. So maybe some cool things there, but we haven't been able to look at it in any kind of meaningful way.
Great. And then we've got a question, actually a handful more that have popped in the chat. One from Abba saying, thank you for a great presentation. Are seismic lines found in any other regions of the world? How long does it take for native woody vegetation to come back naturally in these areas without restoration and intervention?
Yeah, so seismic lines exist in Russia for sure, but also, and I did not know this, in Australia. Apparently it's a very big problem in Australia, particularly for dingoes, where they're seeing the same kinds of things. So I've been in contact with a researcher out there on those things, but it's far less, they understand it less than we do, probably because caribou. But yeah, certainly seismic lines do exist in other places, certainly in the United States as well, less density. There is no known time for these features to grow back. I guess, actually, I don't want to guess on how many are regenerated. It's very, very, very low. There's no indication that it's time-based because it depends on how it was cut, when it was cut, what the machinery was, how often it was reused after that. And the majority, like over 90%, I would guess, of these lines just aren't recovering despite having been created in the 80s. Like they're just not regenerated. They've stagnated at wetland raminoids. We're actually currently running a program where we've collected high resolution LiDAR across the entire boreal of Alberta, and we're quantifying the recovery rates of these features and classifying the vegetation. So that's a really cool thing that we've got going on now to understand the magnitude of the restoration that needs to happen.
Great. And then we've got a question from Colleen that's maybe getting more at how that restoration actually happens when it does. So could they interrupt the linear features for shorter stretches, like making an underpass under a busy road? Colleen's wondering if this could be an intermediate restoration step that would reduce the speed of wolves in hunting by providing corridors for caribou, and maybe be done on a smaller number of kilometers at first, and be done a little more quickly than on the way to like a full restoration of those linear features.
Yeah, that's certainly something that people are playing with. The one that I showed was very much a full line being recovered. That same group, that picture was taken by Jesse Tigner with work done by a First Nations group in BC. They're also playing with the idea of, 100 meters restored, 100 meters not, 100 meters restored. The problem with doing that kind of approach, or even more piecemeal than that, is the biggest cost of restoration is getting to these areas to begin with. And if you go and restore bits and pieces, you're then going to have to redisturb it to get back into that landscape. So you have to be pretty darn confident that you're going to get the effects that you want and not have to go back in there for that to be worth it. And with the precautionary principle, we're kind of just trying to restore as much as we can, as efficiently as we can. Some groups have also tried to do just structural regeneration. So things like tree felling or grabbing coarseway debris and putting it on the lines, log rollbacks, even fences to break up that hunting efficiency by wolves. But then it's again, well, I mean, we're there, so do we also plant trees and try to return forest cover? Because those smaller or shorter term techniques are going to break down eventually. So we don't have a great way out yet, but certainly that's something people are thinking about.
Great, and then it looks like we've got a question from Todd. So Todd's wondering, do you know if other mammalian predators exploit these linear features in a similar manner? Or perhaps some species might avoid them, such as a marten or a lynx.
Yeah, so we think that cursorial predators are going to be the most benefited by these landscapes because they rely on encounter rates and traveling to encounter their prey. We don't have a ton of them in the system. We know bears will use these lines to facilitate movement a little bit, and will also forage on the lines because blueberry in particular and some other shrubs grow back on the features, very low lying, so they'll eat them. Everybody, all of the critters more or less will use the features for movement. Caribou will even use the features for movement. Moose will use them. So we do have GPS color studies looking at that. We also have a ton of cameras out on these landscapes. One anecdotal recent piece of evidence that we have is that we're finding lynx are using them less, which kind of fits with, they're a little bit more sit and wait, think cursorial, somewhere between. But yeah, so most critters will use them for movement. There's very little risk there as far as like humans go, but we think that the biggest impact is through wolves because they're cursorial predators.
Great, and then you mentioned that one of the sort of missing links there is trying to assess how kill rate's actually shifting. What sort of predation monitoring is going on across these sort of landscapes that vary a lot with linear features? Because it's such a big study area that I feel like it'd be really hard to like coordinate all of that.
Yeah, so there was a little bit of kill site investigations going on in one of the Alberta programs. It wasn't very much. Then there was some in another one, but largely nothing. So I could look at cluster analysis and infer kill rates, but I don't have enough data to actually parse out rest areas from kill sites and ground truth that. There's very little ground truthing data. I heard a rumor that there might be some kill site investigations coming in BC with newly collared animals. And if that's the case, I'd really like to work with those guys to see if we can ground truth and then be able to extrapolate that to these other study systems where we don't have enough data. But that's the limitation. I mean,
Yeah.
kill sites are hard.
Great. And then it doesn't look like we have any other questions in the chat. But again, if anyone does have a question, feel free to drop it there or unmute yourself and ask out loud. If not, then we can end here early.
I've got one more quick one. So you have 5-minute location data, which is really nice, really detailed. Have you rarefied it at all and seen if like you can explore some of the questions you've asked and how the results hold up if you were at 20 minutes, at 40 minutes, at an hour?
Yeah, so what I didn't go into is these different study areas, the 4 of them, they had different fixed schedules. The one in southern Alberta, central, still northern Alberta, the most southern of the Alberta ones was the 5-minute location one. The other 2 had 15, Saskatchewan had 3 hours. So we actually rarefied everything to 3 hours for the home range analysis. But when I was working with the 5-minute data and the 15-minute data for my master's, I did play those games of rarefying to find out when I could adequately catch them on linear features, using linear features from like path to path or point to point. And there was like an exponential decay in my ability to catch that. I'd say 15 minutes was totally fine. 5-minute was amazing. An hour you started to do not so well, and 3 hours wouldn't work for that.
Super helpful. Thanks.
Okay.
All right. Any other questions?
If anybody has any ideas on how I could get to the kill site stuff, or if you would believe a kill site cluster analysis without the ground truthing data, I'd love to hear that, because I haven't been doing it because of that reason. So if anyone has anything to talk about with that, I'd love to hear from you.
Yeah, so I see Joe pointing there. So my second chapter is actually doing exactly that, of developing predictive cluster models and testing out the efficacy of different approaches. So I'd definitely love to connect and talk more about that.
Yes, please.
Yeah.
That would be great.
Yeah, for sure. We've got around 15 years plus of cluster analysis data for wolves, and then another 7 from cougars, and doing sort of a comparison there. So yeah.
Amazing.
Yeah, I'd
and
love to
I
chat
think
more
that-
on that.
That's it.
I think the system Jack's focusing in will be useful. If it depends, I think on prey items, particularly the biomass they're getting from those, and time spent at larger prey versus smaller, and you would know some of this. So you certainly, I think, have promise for simulating, higher probability, larger prey kill sites with more confidence. It's just the smaller stuff that might be missed. Yeah.
Yeah, that's where that tricky part is. If depending on what they're taking more through that facilitation is where it really would come down to it.
Yeah, for sure. And if my thought is that if they're eating smaller prey, facilitation becomes more important. And that's just totally pie in the sky ideas at this point. But you'd imagine if you need to eat lots of things, you need to be able to move faster to get from beaver lodge to beaver lodge. Whereas if you can sit on a moose for a couple weeks, maybe it's less important. But I haven't been able to test any of that, obviously.
Yeah, that would be where, if it's facilitating, and even for things like bears, if it is facilitating movement, especially during things like calving seasons for these different species, that's where you'd see maybe a really big effect of increasing that ability of, I mean, bears find calves really efficiently anyway, But if it
Yeah.
really increases it for, say, wolves, that would be big. Yeah.
Yeah, and the recruitment rate of caribou in many of these populations is next to zero because all the calves get eaten by wolves.
Yeah.
Primarily wolves, also bears a bit, but yeah, that's huge.
Yeah, for sure.
Do you have any evidence that indicates some of these lines might be a bit of a poor choice for calving? Are they calving only in high grass or brushy areas associated with the edge of the lines preferentially? So that encounter would actually be facilitated by a different mechanism?
So there is evidence that linear features also facilitate use of peatlands, i.e. low productivity caribou habitat. So it is bringing wolves in, but caribou are not selecting linear features or near linear features to calve, but they have no choice. Like you saw that landscape, they're close by no matter what. So
Yeah.
as long as the linear feature is increasing the use of peatlands in general by predators, that is a problem. But it could just be that they're cruising right through those peatlands and not necessarily paying attention to what's beside. Don't know. There's a little bit of work looking at whether or not they're killing more often near linear features. Not super clear across papers, or generally the story is a little bit muddled to me still.
Thank you. Great
Yeah,
stuff.
thank you so much. That was a really, really fantastic talk.
I tried to
Yeah.
get y'all out of here early, but here we are.
Well, it was a good talk, facilitated a lot of great discussion. So
Good. Glad. Feel free to reach out. I put my email in the chat. Thanks everyone for being here.
yeah, thank you again, and I'll reach out separately to chat more about cluster stuff.
Yes.
But yeah, thanks again, Melanie.